It's Mr. Lawrence here, and we're going to be building off of our linear exploration. We're going to try to find some applications in the real world with this stuff, because the math is just theoretical and kind of cool if you can't apply it to real situations. Now, it's going to require you to do some thinking and analyzing, and there'll be some cases that there may not be one specific answer, but you will need to be able to think and not just regurgitate. Some of you are going to have a hard time with that. I'm going to be honest with you. You just want to give the answer and move on to the next thing. I'll give you a hint. You ain't help. Talk to my pre-algebra kids. They're eating this stuff up. I tell you, if they can do it, so can you. It's all about the attitude you have. Some words you're going to hear me use are lines of best fit, correlation, scatterplot, maybe some other definitions I throw at you as well. So let's get to it. Let's see a problem here. I have this data which shows the missing days in a quarter for some students and their GPA for that quarter. And I'm going to make a scatter plot of this data. Now, a scatter plot is not a connect the dots page, okay? It's not that. We're not going to connect the dots. We're going to plot these points, and it looks like I'm too big here, so let's see if I can get it on. Oh, that looks a little bit better. Yeah. I need to go a little bit further. Maybe I'll even go smaller than that. Oh, well, that ought to work. Okay, now, when you're making your scatter plot, it is important to know which variable is your independent variable and which is your dependent variable. Well, I'll give you a hint. The independent one causes the dependent variable. Okay? So do you think the GPA causes the number of days a kid misses, or do you think the number of days might have an effect on their GPA? Well, this is your independent variable. Your independent variable is always your input in your input-output table. It's your X. Okay, that forces the GPA to be your Y or your dependent variable. Okay, dependent variable. Okay. Now, when I make my scatter plot, I'm going to have to set a scale here. And I have to space it out evenly, and I want to use as much of the graph as I can. I notice that my minimum is 0, my max is 7. And I have, how many lines here? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I have 18 lines. So I might make every 2 lines 1, but I can't change. I can't decide to go, you know, I'll make this 1 and then this one 3, like the right I did there. That's a mistake. So 2, that'll be 3. Okay, 4 days missed, 5 days missed, 6 days missed, 7 days missed, and then 8 days missed, and of course this would be 9 days missed. Now, I know right off the bat that some of this graph will be wasted data, wasted graph, but I can go ahead and use it. I don't want to have too much wasted data. I want to minimize it. All right, I'm looking at my GPAs, and they go from 1.8 all the way up to 4.0. And again, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 lines to use. Well, I don't need to show anything below 1.8, so I might just kind of go like this, and that way it'll allow me to start at a different number. Now, I may actually, for the sake of spacing things out evenly, I might call this, you know, 1 5/10. And then let's see, what if I go up 3, 1, 2, 3, 2.0, 1, 2, 3, 2.5, 1, 2, 3, 3.0, 1, 2, 3, 3.5, 1, 2, 3, 4.0. And hey, that's going to work out pretty good. But I had to put this little thing in here because this block looks like I'm counting by 1.5s, whereas here I have 2 blocks counting 1, 2 blocks counting another one, 2 blocks to get another one. I'm not going to be doing each block as 1.5. So 1, 2, 3, this will be a 2.0. And then 1, 2, 3 would be a 2.5. right? 1, 2, 3 is going to be a 3.0, and then a 1, 2, 3 is a 3.5, and then here is going to be a 4.0. Okay, now there's going to be very little wasted graph. I'm very pleased about this. You want to make sure you're spreading things out. The only wasted part of my graph will be over here. Now you normally wouldn't highlight it, but I'm going to show you that we want to minimize the wasted space. We don't want to cram the graph into a little corner and say, well, I did it. We want the line to be spread out as evenly as possible because otherwise it looks distorted. Okay, it might mislead the reader, and we'll talk more about that in the next several coming days. All right, so let's see here. Okay, I'm just going to leave that highlighted for now, and I'm going to plot these points. And let's see here. Let me scroll up. Oh, I forgot something very important. I didn't label my axes. I have to tell the reader what is going on. So this is the days missed in the quarter. And then this over here is the GPA. All right, for the quarter. So I guess I can make that look a little bit better, make it look a little more like a G. All right, so I'm going to plot some points here. Looks like I'm going to have a point at 0, 3.7. So 0, 3.7. Well, 3.75 would be smack in the middle. 3.7 is going to be right about there, right? Okay. All right. I need one at 3, 4.0, so there'd be a point there. Let's see here. I need one for 4 days at 3.5. And then I need another one at 4 days at 2.7. Well, 2.75 would be smack in the middle, so it's just going to be a little bit below. All right, now 7 days, there's a 1.8 GPA. 7 days, let's see, 1.75 would be smack in the middle, so it'll be a little bit up. Okay, and then at 1.5 days, 1.5 days, which would be here, the person's GPA is a 2.9, so it's going to be something like that. Okay, now this data doesn't look very linear, does it? No. And we're going to talk about what that means. Sometimes your data will be nice and tight, or it'll look very linear. In this case, we're going to draw a line of best fit. Now, this isn't a great example in terms of getting a real linear prediction, but we still will try to do our best drawing a line of best fit. Now, there's some rules you got to follow in drawing a line of best fit. The most important rule, despite what most kids think, the most important rule is follow the path of the points. Okay? If the points are going like this, well, my line of best fit better be going roughly in that direction. If my points are going like this, and those seem very linear, then my line, of course, would go down something like that. Okay, number one is follow the path of the points. Number two, you want to minimize the distance from the line to the points. You want to minimize the distance. Okay, get them as close as possible. Like, for example, taking this one here, this would be a bad choice because the points are all getting farther and farther away. There's two that are really close, but then these two are further. If I put it more around there, then I've minimized the distance. Okay, now the third one, and unfortunately, this is the one kids remember the most, and they do it first. Don't do it first. Is you want to split the points evenly. Okay, you want to split the points evenly. So if you can, like up here we have 5 points, maybe my best fit will look like this because there's 2 points above it, 2 points below it, and I'm going through that point right there. Over here, same idea. This one I might actually have to change the path of the line a little bit. Let's see here. Probably no. That would maximize some distance. Oh, that's not too bad. Oh, but there's 3 on one side and 2 on the other, so maybe I kind of go like this. Yeah, and so we're counting this one as being on the line. I guess I can adjust a little bit more. Oop, I have 3 above and 1 below, don't I? Silly me. I'm having a hard time doing this one. I'll have to take a new approach. Okay. Now, if it's, so linear like this, notice I have 2 above, 1 below, and I'm going through 2 points, I would accept that because sometimes it's difficult to get it exactly the way you're supposed to. All right, so this is not the most important one. By the way, it would be absolutely wrong, I hope you're watching, it would be absolutely wrong to do this and go, hey, I split the points evenly. Okay, because you're not following the path of the points. That would be absolutely wrong. Do not do that. All right, so I've got my data here. I get my line of best fit. I've got 2, 4, 6. I think my line of best fit is going to do something like this, and those two are looking pretty linear to me. I'm going to see, well, I guess I can split them like that. A little bit off here. Yeah, that looks pretty good. These are roughly the same distance. And these are very close, and there's 3 and 3. There's my line of best fit. Okay. I mean, I guess I could try to force it into 4.0 range there. That might be a little bit better. Okay. Anyway, so I'm following the path of the points. I'm trying to minimize the distance as best I can. And now I am dividing the data evenly. Okay, now when I read this, I can use this to make predictions. Oh, by the way, the slope is going downward, right? That means the data has a negative correlation. It has a negative, the line of best fit, correlation. What does that mean? Well, that means as x gets larger, you see x getting larger in this direction, what's happening to y? Y is decreasing. Sure it is. Look. Let's get a nice big point here. Okay. If I'm here at 0, x is small, right? And y is bigger. What happens when I go to where x is 5? My y value dropped from 4 to 2.5. My x value increased, my y value decreased. Okay. By the way, the negative correlation could also mean that if x is decreasing, then y is increasing. Now, it's important to note that correlation does not mean causation. I can tell you that there's a positive correlation between the number of storks in the Seattle, Washington area in the 1970s and the number of babies born. It is true, but correlation does not mean causation. Okay, if you think about it, you might be able to figure out what caused the storks to go up as the babies came. It wasn't storks causing babies. Okay, if you're not sure why that's funny, ask your parents about the old tale parents used to tell their children about where babies come from. Anyway, so this line has a negative correlation, okay, not causation. Now I can use it to make predictions. Let me get rid of my orange circle here. Let's say I want to predict the GPA of a student that missed, let's pick a number in here, let's say 6 days. 6 is not in my data. Let's pick 6 days. So 6 goes up here. And what's the y value there? Well, okay, now let's remember that this number, like smack in the middle right here, would be a 2.25. So we're looking at a 2.1 something. So my prediction, I predict that if a student missed 6 days, they would earn about 2.15 GPA. Now, if somebody's line of best fit is a little bit different than mine, but they still follow the rules as best they can, especially since this data is not very linear, they might have a different prediction. Okay? By the way, we could predict the other way too. We could say, what do you expect the GPA to be? Or excuse me, how many days do you expect a student to have missed if their GPA is, say, a 3.25? Well, let's go over here, 3.25. I hit the line, and then I'm going to come down here like this, and look at that. It looks like I'm at 2.5. So I would expect a student with a 3.25 GPA to have missed about 2.5 days based on this data. All right. I'm not going to do tons of examples of this. We're going to get lots of practice of this in class. So I'm going to leave the video as is right now, and I will say goodbye. Mr. Lawrence signing off. Hopefully see you Monday morning. Good night, everybody.